Swayam Prabha. Digital India. Educated India.
Hello and welcome to Lecture 6 on Special Relativity. Today, we will see some remarkable predictions of special relativity on the properties of a light beam as seen by two different inertial observers. These effects are aberration, that is, an apparent difference in the direction of motion of the light beam as seen by a moving observer, and the Doppler effect, that is, a difference in the frequency of a light beam as seen by one observer who is moving with respect to another. These two effects are also expected in Galilean relativity, but however we will see that there is a difference between the effect that we expect in Galilean relativity versus the effect that we expect in special relativity. Moreover, there is a striking, remarkable prediction of special relativity, which is the so-called transverse Doppler shift, which is when you have a source which is moving perpendicular to the direction of relative motion between the source and a detector, you would still see a Doppler shift in the frequency of light. This is something that's completely unexpected from the point of view of Galilean relativity. So let's begin by first discussing the effect of aberration. Now let's consider what happens to a plane wave of light which is propagating in some frame, as seen in some frame S prime, where these are the axes x prime and y prime. And let's assume that this light wave is propagating at an angle theta prime with respect to the x-axis, as seen in this frame S prime. Now, when we think of light as a wave, it has wave fronts. So these wave fronts represent the distance between the peak amplitudes of the light wave. So if we write down the light wave as some kind of wave, which is of the form a times the sine of omega t minus k dot x. Omega tells us the frequency of the wave. The vector k is, or the magnitude of the vector k is what we call the wave number. And this is related to the wavelength of the wave, as k is 2 pi over the wavelength. And the way to think of this wave that is propagating here is to think of it as propagating along the direction k hat. K hat gives you the direction of propagation. And now this quantity in here, omega t minus kx, this is the phase of the plane wave. Okay, so when this phase is an even multiple of 2 pi, okay, so if phase is 2 pi times n, you have a peak in the wave. So what this looks like, if I just plot a snapshot in time, so I fix a time instant and then I just plot what this wave looks like or what the amplitude of this wave looks like, okay, along this direction, what I would see is there's a peak, and then there's a trough, and then there's another peak. And the separation between these peaks is 2 pi over, is lambda. Okay, that's a physical distance between two peaks. Okay, as measured in the frame S prime. And so if you continue to draw the wave, you can think about wave fronts. Okay, so these wave fronts describe the locations of the peak. So for clarity, let me just draw the wave in yellow, and let me sketch the wavefronts in green. Okay, so this represents a series of wavefronts, and let's imagine that the wave is propagating in this direction. So if it's propagating in this direction, you can easily see that k hat is just this, the unit vector in this direction. So that unit vector can be easily written down in terms of its x and y components. So the unit vector is cosine theta prime in the x hat direction plus sine theta prime in the y hat direction. And therefore the phase of this wave can now be written as omega t minus cosine theta prime x prime plus sine theta prime y prime, where x prime and y prime are the coordinates of the point for which you're trying to talk about the position of the wave at which you're trying to figure out its phase. And now this is only, this part here is k hat dot x vector. So I need to multiply this by the magnitude of k if I want to get this term. And the magnitude of k, as we've seen, is 2 pi over lambda. So I'll just write this out, 2 pi lambda. And the angular frequency, omega, is related to the frequency nu. Okay, so this is the frequency. This is more precisely, omega is more precisely the angular frequency. And so we can write the entire phase in this way. We can write 2 pi times nu times t, where nu is the frequency, and we can pull out the factor of 2 pi as common. Okay, so this is what we have for the phase of the plane wave. Now, if the wave is propagating, okay, so the wave is propagating with a speed c, nu describes the frequency of oscillation of the phase of the wave at a particular location. Okay, so nu describes the frequency of oscillation at a fixed x or a fixed position. And therefore, you already know how to think about this as a plane wave. So nu is related to 1 over the time period for, let's say, the plane wave at this wavefront to make a full oscillation, to go from a peak to a trough and come back to a peak. Okay, so t is the time period of oscillation. And so the speed of the wave would be the time it takes for the wavefront over here to appear to have moved to this position over here. The distance that it covers in one time period would be lambda. Lambda is the distance covered by the wavefront in one time period, and therefore lambda over t would be the phase speed of the wave. Okay, this is the speed at which this peak appears to propagate in the forward direction. Okay, so the speed of the wave would tell us the rate at which this wavefront appears to propagate forwards. And this speed should be c. Okay, for a light wave. For a light wave, this speed is c. Now, one important point is that we know in special relativity now, if we go to a different observer describing the same light wave, so let's write down a second observer. So before we go ahead, let me just make a few small corrections. Since we're talking about the frame S prime, we should rather use x prime, t prime over here, and similarly x prime and t prime over here, since we're describing the position and times at which we're observing this wave fronts as x prime and t prime in the frame S prime. And this is x hat prime, y hat prime, which of course we'll assume that if we take a second observer, their axes are aligned. Okay. And more precisely, let's also put down nu as nu prime. That is, this is the frequency of the wave as seen in the frame S prime, and lambda prime is the frequency of the wave as seen in the frame S prime. So let's put primes on everything. Okay, we don't know for sure if these directions or the wavelengths or the time periods would be the same as seen by a second moving observer. So we're going to work out what a second observer moving relative to the frame S prime would see. So now if we consider a frame S, we'll assume that again the axes are oriented in the same way as observer S prime's axes. And we want to ask, what would observer S see for this plane wave? Okay, what is the equation that would describe, let's say, the phase of this plane wave for them? So the question is, what would observer S see as the phase of this plane wave? Now, both observers, if they're looking at a particular location, so they're looking at a particular space-time point, so if both observers are looking at a particular space-time point, we of course know that they will have different descriptions of the coordinates of that space-time point. But they must agree on the phase of the wave at that particular space-time point. Now, why should that be true? Well, the phase of the wave is related to a physical property of the wave. It tells you whether there's an amplitude maximum or a minimum, and that amplitude maximum could, let's say, trigger some other reaction. So therefore, whether you have a maximum or a minimum or some intermediate phase, both observers should agree on the value of that phase. Okay, so the phase is not relative. The phase is something that both observers will agree on. They will just disagree on the description of the location of that space-time point. And so if they disagree on the location of that space-time point, they might also disagree on the frequency of the wave and the wavelength of the wave. In fact, we would expect them to disagree, since we know that time is measured differently in frame S as compared to frame S prime. And lengths are measured differently, so the wavelength should also change in frame S relative to the frame S prime. However, the thing that should still be the same is the speed of light as measured in the frame S. Okay, so let's now work out what would, let's answer this question. What would observer S see as the phase of this plane wave? So observer S would measure exactly the same phase as observer S prime at the same space-time point. However, observer S would measure a different wavelength and or wave vector k bar, and they would measure a different frequency omega. They would, however, or they should, however, measure the same speed c for a light wave. Okay, this is not true for other waves, but for light waves, they should measure the same speed c. Now, in the frame S, we will assume that the vector k bar has a magnitude 2 pi by lambda, where lambda is the wavelength measured in frame S, and the vector k hat, or the direction of propagation, makes an angle theta with the x-axis. Okay, so this angle theta need not be the same as theta prime. Okay, so which is the angle made by the wave with the x-axis in the S prime frame. So to be more general, we'll assume that k hat makes an angle theta, and therefore the phase of the wave measured in frame S can be written in the form 2 pi times nu, where nu is the frequency measured in frame S, t is the time description of a particular location in the frame S, minus k vector dot x vector. Okay, where nu is the frequency measured in the frame S, t is the location of the space-time point at which you're trying to find the phase, as described again in frame S. K vector is the wave number vector, or the wave vector, again described in frame S, which has a magnitude which is related to the wavelength in frame S, and it makes an angle theta with respect to the x-axis, again as measured in the frame S. And x vector describes the position at which you're trying to describe the phase of this wave. And this again, we should be able to write it as, oops, sorry, I made a mistake. Here we should actually write angular frequency. And when we write it in terms of frequency, we can write it in this way: nu times t minus x cosine theta plus y sine theta divided by lambda. Now, if the speed of the wave as seen in frame S is also c, then we should have that lambda over the time period as measured in frame S should be c, or equivalently lambda times the frequency as measured in frame S should be c. Okay, so over here in frame S prime, lambda prime times nu prime should be the speed c. Okay, so now this phase should be exactly the same as the phase measured by S prime at the same space-time location. So what that means is, if tx and t prime x prime describe the same space-time point as measured or as described by S and S prime respectively, then it should be true that the phases, then nu times t minus x cosine theta plus y sine theta over lambda should be equal to nu prime t prime minus x prime cosine theta prime plus y prime sine theta prime over lambda prime. Okay, this is the statement that the phases agree at the same space-time point. Now we can use our dictionary and write x prime, y prime, and t prime, okay, in terms of x, y, and t. So now we can use our dictionary to write x prime, y prime, and t prime in terms of x, y, and t. So if the frame S prime is moving with respect to S at a speed v, what we then have is the dictionary tells us that x prime is equal to 1 over the square root of 1 minus v squared by c squared into x minus vt. Y prime is y, and t prime is 1 over the square root of 1 minus v squared by c squared t minus vx over c squared. Now let's substitute this into the right hand side of this phase equality relationship. So what we would get, let's plug in here. And so what we would get for the phase would look like this. It would be 2 pi over lambda prime x minus vt. I will just put a factor of gamma over here, where gamma is 1 over the square root of 1 minus v squared by c squared, plus, times cosine theta prime plus y divided by y sine theta prime divided by lambda prime plus gamma times the frequency prime times t minus vx over c squared. So this is the phase of S prime, or the right hand side of that equality. And now we can collect all the terms which have x in them. So we collect all the terms which have x in them, and we can write them like this: gamma cosine theta prime by lambda prime. There's an x here, and then there's an x over here. So we can write this as, we can pull out the gamma common to both those terms. So gamma cosine theta prime lambda prime minus nu prime v over c squared, and then times x plus, now we'll collect the terms with y. There's only one term, which is sine theta prime by lambda prime. And we collect all the terms with t. So first we'll write this one plus gamma times nu prime, and then we take this one minus v over lambda prime cosine theta prime times t. Okay, so this is the phase, and this phase, so now we equate to the phase as seen by S, and that phase is 2 pi x cosine theta by lambda plus y sine theta by lambda plus nu times t. I think I made a few sign errors here. This is minus the frequency, so I'm just going to write this as minus sign. So that would correct the sign over here, and there would be an overall minus sign here and a plus sign over here. Okay, so now the thing is that these phases should be equal at every space-time point. Okay, so what that means is the coefficient of x should agree. The coefficients of x on both sides, that is, this coefficient should be the same as this coefficient. And similarly, the coefficients of y and t should agree. So what that gives us is gamma times cosine theta prime over lambda prime plus nu prime v over c square is cosine theta by lambda and now equating the coefficients of y, sine theta prime by lambda prime is equal to sine theta by lambda, and equating the coefficients of t, we get gamma times nu prime plus v cosine theta prime by lambda is equal to nu. And now we can use relationships between nu prime and lambda prime. So using the fact that c is equal to nu prime lambda prime, and using the definition of beta, which is v by c, we can rewrite these equations in the form gamma times cosine theta prime over lambda prime plus beta over lambda prime. So I'm just going to pull this out common. Beta over lambda prime. So this is just rewriting this first equation is equal to cosine theta over lambda. And the second equation is sine theta by lambda prime is sine theta by lambda. And the third equation is gamma times, sorry, this is lambda prime. So this can be written as c over lambda prime plus beta c cosine theta over lambda prime. So again, I'm going to pull out the lambda prime as common. And if I divide both sides by c, then I can write this as 1 plus beta cosine theta is equal to nu over c. Or rather, if I move the c over here and write c by lambda prime as nu prime, then I can write a relationship between nu and nu prime as this. Okay, so there are three things that we want to solve for. We don't know the wavelength as measured in frame S. we don't know the frequency as measured in frame S, and we don't know what angle theta the wave makes with respect to the x-axis in frame S. Okay, so we need to solve for these. Sorry, just some primes missing over here. There's a prime over here, and there's a prime over here. Now, we want to solve for these in terms of lambda prime, nu prime, and theta prime. But we also have a fourth relationship, which is lambda times nu is c. Okay, or which is the same as lambda prime nu prime. And therefore, we actually have four equations that we have, which we can use to solve for lambda, nu, and theta. And that must mean that one of these equations is redundant. Okay, so what we can do is we can divide let's just number these equations. So 1, 2, 3, and 4. So to solve for theta prime, we can just simply divide equation 2 by equation 1. And what that gives us is sine theta prime over gamma times cosine theta prime plus beta is equal to tan theta. Okay. And the last equation tells us nu in terms of nu prime. So this is an equation which solves for theta. Okay, so this is the solution for theta, or tan theta is equal to sine theta prime square root of 1 minus beta square over cosine theta prime plus beta, where I've just used gamma is 1 over the square root of 1 minus v square by c square. Okay, so this tells us the solution for theta, and the solution for the frequency is directly seen from the third equation. Once we know theta, nu is nu prime times 1 plus beta cosine theta over the square root of 1 minus beta. Okay, and the wavelength, of course, is just c by nu. Okay, so what we're really interested in is these two quantities. What is the angle that the light ray makes as seen in frame S, and what is the frequency of the light ray as seen in frame S? Now let's look at this transformation rule and try to understand what the implications are physically for what an observer moving with respect to the frame S prime would see. So here is the frame S prime. This is the x direction, this is the y direction, or if you like, x hat prime and y hat prime directions. And here is the light beam as seen in the frame S prime, and it's moving at an angle theta prime with a frequency which is nu prime. Now let's just first focus on the angle. Okay, so now we have a frame S, and in that frame S, S prime is moving with a velocity beta, or a velocity which is related to beta, as beta is v by c. So in the frame S, S prime is moving with the speed v by c, or alternatively, in the frame S prime, S is moving at a speed which is minus v by c, or equivalently minus beta. Okay, so S has a speed which is minus beta. And now let's look at our transformation law. Okay, so our transformation law tells us that according to observer S, This light beam will not appear to make an angle theta prime with respect to the x-axis, but rather, according to observer S, according to observers in the frame S, the light beam will rather appear to make a different angle. Let's look at it like this, and we'll call this theta. Okay, so this is what S would see. That is, they'd see a deflection in the angle, or the angle would look different compared to what S prime sees. And now what we'd like to understand is how this angle theta changes as we imagine the speed beta of the observer's S changing. So let's look at our transformation formula. Let's copy that down here. So we have tan theta is equal to sine theta prime into the square root of 1 minus beta square over cosine theta prime plus. Now let's look at a few interesting limits of this transformation. Okay, so let's consider a few cases. Okay, the first case is the limit beta goes to 0, or beta is equal to 0, where S prime and S are not in relative motion. And in this case, you'd see that the right hand side just becomes tan theta prime. And of course, what we know physically must be true, therefore, is that theta is theta prime. Okay, and what that tells us is, of course, that there is no deflection because both these observers are at rest with respect to each other. However, let's consider other interesting limits. So let's consider the limit beta goes to minus cosine theta prime. So in this limit, what we're saying is the speed v of frame S prime is equal, or v by c of this frame S prime with respect to the frame S is equal to minus cosine theta prime, or minus v by c is, or let me write it this way, or minus v is c cosine theta prime. Now let's understand what this means. So c cosine theta prime is the component of velocity of the light beam as seen in frame S prime along the x-axis. Okay, so it's the component of the light beam along the x-axis is c cosine theta prime. And now what we're saying is, if we take the limit where the speed v, or the speed minus v, which is the speed of S relative to the frame S prime, if that speed is equal to c cosine theta prime. So what that means is, imagine that you're in frame S prime, and now you have a frame S which is moving to the right with a speed which is exactly the same as the component of the speed of this light beam along the direction of motion. Okay, in this limit, what you would get is, if you look at this equation, if cosine theta prime if beta is minus cosine theta prime, in that limit, the right hand side, the denominator goes to 0, which means the entire thing goes to infinity. So in that limit, tan theta goes to infinity, or theta goes to pi by 2. So in that limit, in frame S prime, okay, the light beam would appear to travel perpendicular to the direction of relative motion. That is, it would travel in the direction y hat. Sorry, and this is in frame S, not in frame S prime. In frame S, the light beam would appear to travel in the direction y hat. So in other words, in the frame S, you're actually able to catch up with the speed of the light beam along one component of motion. Okay, you can't catch up with its speed, along the direction of motion, because that speed is c, and we discussed that the speed limit of any observer relative to another would be c. But however, it is possible to catch up with a component of the speed of this light beam. And in that case, the light beam would appear to stall. Okay, that is, it would not appear to be having any forward relative motion with respect to S. So S is keeping pace with wherever the front of the light beam is. So if the front of the light beam is here, let's say a particular observer in S is over here. If the front of the light beam moves here, the particular observer in S is here. If the front of the light beam moves here, the particular observer in S is here. So relative to that particular observer, the light beam is only moving perpendicular to them. Okay, so that is, if I look at that particular observer in frame S, they are at rest, and the light beam is always, okay, just moving in the perpendicular direction. Okay, that is why the angle theta as seen by them would just appear to be pi by 2. So in other words, this limit corresponds to catching up with the light beam along the direction of motion. All right, and you can see that in this limit, in this limit, if you take theta prime is 0, that is, the light beam is just moving along the x-axis. Okay, it's just moving along the x-axis. Then, of course, the speed v with which S would have to move would go to c. Okay, so that is, you would really have to get close to the speed of light, and in the limit that theta prime is exactly 0, to catch up with the light beam, you would actually have to be traveling with the speed of light itself. Okay. All right. Now let's go to a third interesting case. So first case was beta is 0. Second case was beta goes to minus cosine theta prime. And let's go to a third interesting case, which is the limit where the speed actually does go to c. Okay, or beta goes to 1. I'll just correct a few signs here. So this is, since v is a vector, minus v is what we want to go towards c. So minus v goes to c. Okay, so here we're not forcing theta prime to be 0. We're just asking what happens in the limit where the frame S is moving very close to the speed of light along the direction of relative motion. Now, along the x direction. Okay, so in that limit, first of all, when at some particular speed, okay, so for example, let's take theta prime is 45 degrees. Okay, let's take an example. Theta prime is 45 degrees. Cosine theta prime would be 1 by root 2, which is about 0.7. So when or beta goes to minus 1. When beta becomes very nearly equal to 0.7, at that point you have overtaken the light beam in the x direction. Okay, so the frame S would have overtaken the light beam in the x direction. In this limit, the light beam would appear to be perpendicular. And now if you increase beta, or the magnitude of beta, towards 1, in the frame S, the light beam would actually appear now to travel oppositely in the x direction. That is, it would travel along the negative x direction, because you've actually overtaken the light beam in the x direction. Okay, so in this limit, you overtake the light beam in the x direction. Okay, and in this limit, you just caught up with the light beam, or keep pace with the light beam in the x hat direction.